ಶುರು ಮಾಡೋದಾ ಸರ್?
Yes, start ಮಾಡುವ.
So
Good evening, students.
Sir?
I will start
No, sir. Just I give some
introduction. Okay.
yes, sir. Introduction about you, sir.
Okay. Okay.
ಸೊ ಇವತ್ತಿನ ವಿದ್ಯಾರ್ಥಿ ಪ್ರತಿಭಾ ಶೋಧ ಯೋಜನೆಯ ನಮ್ಮ ಉಪನ್ಯಾಸಕರಾದಂಥ ಡಾಕ್ಟರ್ ರಿಚರ್ಡ್ ಗೋನ್ಸಾಲ್ವಿಸ್ ಅವರನ್ನ ಈ ಒಂದು ಕಾರ್ಯಕ್ರಮಕ್ಕೆ ಸ್ವಾಗತಿಸುತ್ತಾ ವೆಲ್ಕಮ್ ಟು ಯು ಸರ್.
Thank you.
ಸೊ ಅದೇ ರೀತಿ ನಮ್ಮ ಅಕಾಡೆಮಿಯ ನಿರ್ದೇಶಕರಾದಂಥ ಡಾಕ್ಟರ್ ಎ ಬಿ ಬಸವರಾಜ್ ಅವರನ್ನು ಕೂಡ ಈ ಒಂದು ಕಾರ್ಯಕ್ರಮಕ್ಕೆ ಸ್ವಾಗತ ಮಾಡುತ್ತೆ. ಮತ್ತೆ ಈ ಒಂದು ಕಾರ್ಯಕ್ರಮವನ್ನು ಆಯೋಜಿಸಿ ನಮಗೆ ದಿನನಿತ್ಯ ಸೂಚನೆ ಸಲಹೆಗಳನ್ನು ನೀಡುತ್ತಾ ಬಂದಿರುವ ನಮ್ಮ ಅಕಾಡೆಮಿಯ ಮುಖ್ಯ ಕಾರ್ಯನಿರ್ವಾಹಕ ಅಧಿಕಾರಿಗಳಂತ ಡಾಕ್ಟರ್ ರಮೇಶ್ ಸರ್ ಅವರನ್ನು ಕೂಡ ಈ ಒಂದು ಕಾರ್ಯಕ್ರಮಕ್ಕೆ ಸ್ವಾಗತಿಸ್ತಾ ಇದ್ದೇನೆ. ಹಾಗೆ ಈ ಒಂದು ಕಾರ್ಯಕ್ರಮಕ್ಕೆ ಇವತ್ತು ಅಟೆಂಡ್ ಆಗಿರ್ತಕ್ಕಂಥ ನನ್ನ ಎಲ್ಲಾ ವಿದ್ಯಾರ್ಥಿ ಮಿತ್ರರು, ಲೆಕ್ಚರರ್ಸ್ ಮತ್ತು ಟೀಚರ್ಸ್ ಕೂಡ ಈ ಒಂದು ಕಾರ್ಯಕ್ರಮಕ್ಕೆ ಸ್ವಾಗತ ಮಾಡುತ್ತಾ ನಮ್ಮ ರಿಚರ್ಡ್ ಗೋನ್ಸಾಲ್ವಿಸ್ ಅವರ ಬಗ್ಗೆ ಒಂದೆರಡು ಮಾತುಗಳನ್ನು ಹೇಳ್ತೇನೆ. Dr. Richard Gonsalves is an associate professor in the Department of Chemistry of Centralized College, Autonomous, and he has 36 years of rich experience. Presently, he is a director of PG Science Block, LCHRI, and he is the co-author of 7 books, and he has published more than 26 national and international publications. And he also have some degrees like MSc, MA, MBA, MPhil, and PhD degrees as academic qualification. Sir has already guided one student for her PhD. He is currently guiding 3 students for their PhD under Mangalore University. Recently, he has been awarded a national award by AACHE as Best Innovative Faculty in 2021. Okay, thank you, sir. Over to you.
Thank you very much. Yeah. Good evening, students. Today I will be taking an important topic called solutions, which come in the second year PUC chemistry topic, solutions. Let me just introduce the topic like this. When you put little salt, you take little salt, put it into a beaker containing water and stir. First we get a clear solution. It looks like water, but when you taste it, it becomes sweet. But otherwise it looks clear like water. That we call it as solution. Therefore, what is a solution? Let me start with. Solution is a homogeneous mixture of solute in a solvent. Solution is homogeneous mixture of solute in a solvent is called solution. We know that matter exists in 3 states. Solute can exist in 3 states. Solvent can exist in 3 states. Totally 3 by 3, totally 9 types of solutions are possible. Which are the 9 types of solutions possible? Let me share the whiteboard so that I can write. Yes. I have the whiteboard there. I will start writing on. You can see. Let me start. Solutions. What are the types of solutions? I can put 9 types of solution. I will put solute here. Solute. L. And here I will put solvent. Solid, if it is a solute. Solvent is also solute. Solid in a solid. What is the difference between a solute and a solvent? solute is present in small quantity, solvent is present in large quantity. ಯಾವುದು ಹೆಚ್ಚಿದೆ ಅದನ್ನು ಸಾಲ್ವೆಂಟ್ ಹೇಳ್ತಾರೆ, ಯಾವುದು ಕಡಿಮೆ ಇದೆ ಅದನ್ನು ಸೊಲ್ಯೂಟ್ ಅಂತ ಹೇಳ್ತಾರೆ. ಸಾಲಿಡ್ ಇನ್ ಎ ಸಾಲಿಡ್ ಈಸ್ ಎ ಸಾಲಿಡ್ ಸೊಲ್ಯೂಷನ್. ಎಕ್ಸಾಂಪಲ್ ಇಲ್ಲಿ ಬರೀತೇನೆ. ಇಟ್ ಕುಡ್ ಬಿ ಕಾಪರ್ ಅಂಡ್ ಜಿಂಕ್. ಇದಕ್ಕೆ ನಾವು ಹೇಳ್ತಾರೆ ಬ್ರಾಸ್. ಬ್ರಾಸ್ ಇಸ್ ಅನ್ ಎಕ್ಸಾಂಪಲ್ ಆಫ್ ಕಾಪರ್ ಅಂಡ್ ಜಿಂಕ್. ಸಾಲಿಡ್ ಇನ್ ಎ ಲಿಕ್ವಿಡ್, ಇದಕ್ಕೆ ನಮಗೆ ಶುಗರ್ ಸೊಲ್ಯೂಷನ್ ತಗೊಳ್ಬಹುದು. ಶುಗರ್ ವೆನ್ dissolved in water, it gives sugar solution. This is coming under the second type solution. Third one, I will take solid in a gas. If there is a solid distributed in a gas, I can put iodine, which is brown color, in nitrogen. If I put, then it is a solution of iodine in nitrogen, solid in a gas. Similarly, I can go for now 3 more. Liquid in a solid, liquid in a liquid, liquid in a gas. 3 more combinations. Liquid in a solid, I can have liquid, solute, and solid. You can have amalgam, sodium amalgam. Amalgam is a mixture with mercury. Mercury is put in sodium. Liquid in a liquid is alcohol and water. Alcohol and ethanol. Ethanol. Liquid in a gas, I can take an example of a liquid in gas. If you put benzene vapors in nitrogen or any other liquid droplets in nitrogen, then it will be liquid in a gas. We can go for the last varieties: gas in a solid, gas in a liquid, and gas in a gas. 3. When you go for gas in a solid, it will be an example of hydrogen adsorbed on palladium, platinum, nickel, etc. These are examples. Gas in a liquid is a carbonated drinks, carbon dioxide in water, soda water. And gas in a gas is our air. Air is a mixture of gas in a gas. Nitrogen and oxygen both are present in the atmospheric nitrogen and all that. This is about types of solution we are having. Now we move on to how do you express the concentration of a solution? What is the meaning of the concentration? Concentration of a solution, when I say, it represents the amount of solute present in a given quantity of solvent. That is called concentration. If the amount of solute is more, I say more concentrated solution. If the amount of solute is less, then I call it as dilute solution. Therefore, strength of the solution is given in terms of concentrated solution and dilute solution. We go to the next slide where we can write. One minute. Hold on. One minute. We are going for a next slide. Yes, we will start. There is a little hitch. Okay. we will be taking up next one. Concentration, as I said, first one we go for molarity. What is molarity? It is capital M. Molarity is number of moles dissolved in 1 liter. Number of moles in a liter. You have learned this in first year. Molarity is number of moles in a liter. The formula would be, to calculate would be W by M, where W is mass in liter and M is molar mass. This is molarity. There is one more called molality, which is given as small m. Molality is number of moles present in 1 kg of solvent. See the difference. Here it is solvent, here it is solution. This is number of moles present in a solvent, 1 kg of solvent. Therefore, molality is independent of temperature. It does not change with temperature. Because both are masses, do not have volume. This is also mass in molar mass, and this is also mass. Therefore, it is independent of temperature. Molality. Molarity over, molality over. Third one, mole fraction. Mole fraction is given by X. What is mole fraction? It is the ratio of number of moles of 1 to the total number of moles present in the solution. Number of moles of 1 to the total number of moles in the solution is called mole fraction. Mole fraction is this way. Mole fraction of solute plus mole fraction of solvent should be equal to 1. This is 1. Fourth one is ppm. Percentage per, parts per million. Therefore, you take mass of solute divided by mass of solution, not solvent, into 10 to the power 6. When do I use this? I use ppm for a very, very dilute solution. I can use ppm. Another one I can use is ppb, parts per billion, parts per million or parts per billion I can use. Then we can use mass percentage. This is mass of solute in mass of solution into 100. In 100, if you calculate, that is called mass percentage. Like that, these are the important methods by which you can calculate the strength of a solution. I said molality is independent of temperature. Mole fraction is also independent of temperature. Molality and mole fraction are independent of temperature. Okay. We move on to the next one. We will go for the fresh board, first page. Okay. What is what is solubility? Solubility. Okay. This is a question. Right, dissolves in water. Again, you put one more spoon, it dissolves. Therefore, I say sodium chloride is having high solubility. But if you put 1 crystal of silver chloride in water and stir 100 ml of water, some amount of silver chloride remains undissolved. That means I will say silver chloride is sparingly soluble, less soluble. Therefore, what is this solubility? Solubility is maximum amount of solute, maximum amount of solute which dissolves in a given amount of solution, in a given amount of solution is called solubility. Solubility has the same unit as mole per liter, mole per dm cube, or it can even be given as gram per liter. This is the unit of solubility. Solubility and concentration are one and the same. Solubility is same as this one. Solubility is expressed per mole per liter. Higher the solubility. When a solute, let us say sodium chloride, is added to water, solubility increases with the increase in temperature. Will it be for all is the question. Sodium chloride, when I dissolve in water, I can increase the temperature and see more things will dissolve. More sodium chloride dissolves. But it will not be the same for others. For example, when sodium sulfate dissolves in water, solubility increases with the decrease in temperature. Please remember, this reaction is different than this reaction. Sodium chloride dissolved in water is, if it is endothermic is favored at high temperature. If this is exothermic, first one, this is exothermic. Exothermic reactions are favored at low temperature. Therefore, not all salts, when dissolved in water, will increase the solubility. There are salts which are exothermic. When temperature is decreased, solubility increases. This part should be known to you. Next comes solubility of a gas in liquid. How do I make a gas to dissolve in water? I will take, there is a law called Henry's law. Henry's law. What the Henry's law says? He says the mole fraction of the gas dissolved in the liquid is directly proportional to pressure exerted by the gas above the liquid. What does it mean? If you put more gas under pressure, more gas dissolves. That is the meaning. If your carbon dioxide is passed under high pressure, more carbon dioxide dissolves. This is called Henry's law. Therefore, if I can put it this way, mathematics, it could be written this way also. P is proportional to X. X is called mole fraction. Therefore, P is equal to some constant called Henry's constant into X. This is called Henry's expression. Please remember this. KH is called Henry's constant. KH is Henry's constant. If KH is more, solubility will be less. If KH is less, solubility is more. This is very important from the CET point of view. If high KH, lower solubility, lower X. Low KH, high X. X is the mole fraction, X will be. Therefore, this is the net understanding of Henry's law. Therefore, what is Henry's law? Let me put it in statement. at constant temperature, the mole fraction of the gas dissolved, X, is directly proportional to pressure of the gas above the liquid. This is called Henry's law. Can we write a graphical understanding of this? If I put a graphical understanding of this, we can show here. Yes. I will draw a graph. Yes. Here I will write pressure. Here I will write mole fraction. What we get here is a graph like this, straight line passing through origin. The slope of the line, we can write the slope. Slope of the line is called Henry's constant slope. Another gas, the gas will be like this. Third gas, the gas will be like this. Straight. Therefore, this will have higher slope. Higher the slope, lesser will be the solubility. Lower the slope, higher will be the solubility. This is the graph you should know. Yes, this is Henry's constant. Next we go for next point we will write here is vapor pressure. What is vapor pressure? I will write P. Can we answer what is vapor pressure? Vapor pressure is pressure of the vapor. Where? Above the liquid surface. Pressure of the vapor above the liquid surface, which is in equilibrium with the liquid. Liquid and vapor should be in equilibrium at a given temperature. Given temperature. This is called vapor pressure. Vapor pressure is the pressure of the vapor above the liquid surface, which is in equilibrium with the liquid. This is called vapor pressure. There is one law called Raoult's law. What the Raoult's law says? If I take a binary liquid mixture, which are two liquids, volatile liquids. I will take two volatile liquids. If you take a binary mixture of two volatile liquids, the vapor pressure of each liquid is directly proportional to mole fraction of that liquid. First liquid is like this. Second liquid, P2, is directly proportional to X2. Where X1 is the mole fraction of the first liquid, X2 is the mole fraction of the second liquid. Therefore, we can write here P1 is equal to K into X1. P2 is equal to K into X2 or K2 into X2. K is a constant. Therefore, this is called Raoult's law. The vapor pressure of each component above the liquid surface is directly proportional to mole fraction of that liquid. Higher the mole fraction, vapor pressure will be higher. Higher the mole fraction, vapor pressure will be higher. This is called Raoult's law. Therefore, if I take two liquids, A and B, I will write here. One liquid is A, then it will be mole fraction of that liquid into a constant. And later we can find out that the constant is vapor pressure of the pure component, pure A. Similarly, I can write PB is equal to mole fraction of B into vapor pressure of pure B or vapor pressure of the pure component B. This is called Raoult's law. Therefore, state Raoult's law. At constant temperature, partial vapor pressure of each component is the product of mole fraction of that component and vapor pressure of the pure component. I repeat again. At constant temperature, partial vapor pressure of each component is the product of mole fraction of that component and vapor pressure of the pure component. This is called Raoult's law. Raoult's law. Now, this is applicable for binary liquids. We'll go to the next. 1 minute. Yes. Based on the behavior of the liquids, I can classify liquids into three types. One is called ideal solution, ideal liquid mixture or ideal solution. Second one is called non-ideal solution. Third one is also non-ideal. Non-ideal solution. One showing positive deviation from Raoult's law. RL I will write. Raoult's law. Another one showing negative deviation from Raoult's law. RL. Therefore, solutions are three types: binary liquid mixture, are three types. At all concentrations and temperature. A solution in which all the components obey Raoult's law at all concentrations and temperatures is called ideal solution. For example, if there are two A and B, mixture is there, A should obey Raoult's law, which is given as PA is equal to XA into P naught A. This should be followed. B should obey Raoult's law. PB is equal to XB into P naught B. This is also to be followed. If these two are followed, then it is called ideal solution. Give me some examples of ideal solutions. If I give you, one would be benzene and toluene. See the difference between benzene and toluene. They are homologous series member. When I say homologous series, they differ by a CH2 group. Benzene and toluene, both aromatic, they differ by a CH2 group. 2. Cyclopentane and cyclohexane. Again differ by a CH2 group. Third one, chlorobenzene plus bromobenzene. The difference is chlorine and bromine, bromobenzene. Hardly any difference. Fourth one, you can write like this so that we can get ethyl bromide, ethyl iodide. Therefore, if there is a slight change between the two, then it should be an example for homologous members. They are there, then they are partners or part of ideal solution. Therefore, easily you can identify which is ideal, which is non-ideal. Now the question is, what are the characteristics of ideal solution? We shall see now. The characteristics of ideal solutions are, let me write. characteristics of ideal solution. Point number 1. The force of attraction between molecules of A and A means one liquid, and B and B is equal to force of attraction between A and B. What does it mean? The force of attraction between the two liquids independently is same when I mix A and B. Force of attraction, there is no change. Therefore, what would happen at the second point? Second point is all components obey Raoult's law. All components, all better. All components obey Raoult's law. This is very important. Third one, during mixing, volume does not change. What is the meaning of this? Volume of mixing does not change. If I mix 50 ml of A with 50 ml of B, total volume become 100. Neither become 99.9 nor become 100.1. It become exactly 100. There will not be any change in volume. V3 is equal to V1 plus V2. That is the meaning. Fourth one, during mixing, there is no change in enthalpy. And enthalpy will also no change. No heating or cooling. There is no heating or cooling observed. And the fifth one, you can easily separate the two components. Two components are separated by fractional distillation. Therefore, distillation. For a CET, a question can be asked here. Which of the following can be easily separated into its individual component by fractional distillation? Just look for ideal solution. The components of ideal solution can only be separated by fractional distillation. This should be kept in mind. Now I will go for, if you can graphically represent, I will go for a graphical representation. Yes, you can see, I can graphically show this here. 1, 2, 3. Should have been straight. Here I will write XA is 0 and XB as 1. Here I will write XA as 1, XB as 0. Here I will write P0 B, pure B. Here I will write, this should have been straight. This is P0 A. It need not be same height. It could be different. I will write here. This is P0 B and this is P0 A. Now what you do is, it will obey Raoult's law. Therefore, you will have a straight line. Sorry. You could have written this way. This I will write P0 A. Okay, don't worry. This will write P0 B. Getting drawing is a problem. Straight. It should be straight. This is P0 B. And now the graph would be like this. This is total pressure PT, which will be equal to PA plus PB. if this is straight line, this is straight line, and this is also straight line, then I call it as, this is mole fraction. This is mole fraction along x-axis. This is vapor pressure along y-axis. If you get a graph straight, then it is called ideal solution. What is non-ideal then? This is ideal. We will put little more here, straight. Okay, straight. We'll go for non-ideal solution, which shows positive deviation from Raoult's law. Take this. Non-ideal solution showing positive deviation from Raoult's law. Let me explain first. Positive deviation means what? If the vapor pressure of each component is greater than the product of mole fraction into vapor pressure of the pure component, greater. PB is also greater than XB into P naught B. If this is the case, then it is called positive deviation from Raoult. When it will happen? The characteristics would be one, force of attraction between A and B and B will be more than force of attraction between A and B. What does it mean? They try to repel each other. That is the first characteristic. Force of attraction is less. Second, they do not obey Raoult's law. Do not obey Raoult's law. Third one, when you mix, the volume will become more than the two. Yesterday, I was just telling you, V3 is greater than V1 plus V2. If you mix V1 and V2, it will not be equal, it will be slightly more. That will be observed. The volume increases during mixing. And fourth one, delta H. What will happen is cooling is observed, not heating is observed. What will happen is when you mix the two, cooling is observed. Delta H is positive, not negative. Delta H is negative is exothermic. Delta H is positive, endothermic. Cooling happens. And fifth one, they cannot be separated by fractional. There is no fractional separation. Fractional separation is possible or distillation is possible. These are the characteristics of non-ideal solution showing positive deviation from Raoult's law. Which are the examples? We will write examples. One, ethyl alcohol and water. This is one example. Second one, methyl alcohol and water. Two examples of alcohol and water I have taken. Ethyl alcohol and water, methyl alcohol and water, non-ideal. Third one is, I will write benzene, third one. Benzene and acetone. Acetone, everybody knows, CH3CO, CH3. Fourth one, ethanol and acetone. Ethanol and acetone. Fifth one, carbon disulfide and acetone. And yes, methanol and acetone. And acetone. These are examples of non-ideal solution showing positive deviation from Raoult's law. Now, how do you separate them? If they are not able to separate by fractional distillation, what is the method? We have to look into this. There should be a understanding, I will explain now. There is a concept called azeotropic mixture. TRO. Tropic mixture. What is azeotropic mixture? Azeotropic mixture is one which distills without any change in without any change in composition. It's called azeotropic mixture. For example, rectified spirit. Rectified spirit has 95% alcohol, 95.5, okay, 95.5% alcohol and 4.5% water. You distill this 100 times also, you will end up in getting 95.5 and 4.5 alcohol and water. Therefore, you are not able to separate this. This is called rectified spirit. Because alcohol and water is showing what deviation? Positive deviation from Raoult law. Therefore, if it shows positive deviation from Raoult law, it will always give an azeotropic mixture. It always ends up in giving azeotropic mixture. Therefore, its graph, if you see now, yes, here I will write XA is 0. Here I will write XB is 1. Here I will write XA is 1. XB is 0. Here I write vapor pressure. Here I write mole fraction X. Here I will write P naught B. Here let me write a little lower, P naught A. Ideal means I will write a dotted line. Dotted line represents ideal. Ideal. It should have been upper. Yes. This is ideal. Yes. This is ideal. Now, what will happen is it will show a positive deviation from Raoult's law mean. Instead of this, you will have a positive deviation up. This one will show also a positive deviation up. Therefore, the sum of this will become like this, up. Above this straight line, you have this also above the straight line. This will be double, it will be. Therefore, P total will be PA plus PB. If you have this graph, then it is showing positive deviation from Raoult's law. This is a solution which shows positive deviation from Raoult's law. Special is, it is called minimum boiling azeotrope. What is the meaning of this? The azeotropic mixture of 95.5% alcohol and 4.5% water will boil below the boiling point of water, which is 100, and below the boiling point of alcohol also. This will boil at 78.13 degree, which is below the boiling point of pure alcohol and below the boiling point of water, it will be boiled. Therefore, it is called minimum boiling azeotrope. Next one. The third variety is called maximum boiling azeotrope, or one showing negative deviation from Raoult's law. When you will have negative deviation from Raoult's law, we'll see. Negative deviation from Raoult's law. What are the characteristics for negative deviation from law? Force of attraction between A and B, A and B should be, attraction should be more than force of attraction between A and B. It's the same. Force of attraction between A and A was A and B and B. Force of attraction between A and B, attraction is less than A and B, not more than, less than A and B. Means they attract each other more. They don't repel each other, they become attract each other more. As a result, what will happen is they do not obey Raoult's law. They do not obey. Third one, when you mix the two, delta V mixture should be less than 0. That means volume decreases. 50-50 become 99. 50 and 50 does not become 100. 50-50 become 99. Fourth one, delta H mixing, heat is liberated. Exothermic. Heat is liberated. And the fifth one, it also the components cannot be separated. As it forms azeotropic mixture. Azeotropic mixture. Please remember, azeotropic mixture is one which distills without any change in composition. The same composition it will retain. That is what azeotropic mixture. This mixture is called maximum boiling azeotrope. That was earlier one was called minimum boiling azeotrope. This is called maximum boiling azeotrope. That means the boiling point of azeotropic mixture is higher than both A and B. That is the meaning of this maximum boiling azeotrope. Now, what are the mixtures? Examples we have to take. Example could be HCl plus water. This is one example. HNO3 and water. This is second example. HCl and water, HNO3 and water, benzene and chloroform. I am writing all this because for CET, one will be asked and then you should be able to identify whether it is from positive deviation or the negative deviation. This is one negative deviation, benzene and chloroform. Fourth one, ether, diethyl ether and chloroform. Aniline and phenol. Aniline plus phenol. These are some of the examples. And last one I can give you is chloroform and acetone, because they had plenty of acetone examples in the earlier. But if it comes with chloroform with acetone, then it is negative deviation from Raoult's law. Please remember. These are the things which show negative deviation from Raoult's law. Now, how the picture would look like graphically, if you plot, how the graph would look like. The graph would look like this. I will draw it. Yes. Here I will write XA is 0. Here I write XA as 1. Here I write XB is 1. Here I will write XB as 0. And here I will write vapor pressure as I did earlier. Here I will write mole fraction, vapor pressure. Here I will write P naught B. Here I will write little lower, I will write P naught A. You take a scale and make a dotted line showing that ideal behavior. You also put a dotted line joining P naught B with the other end. Yes. You put a dotted line joining B and A. This is ideal. Now, non-ideal, you should have an inward curve. The curve would become like this. This curve also goes this way, inward. This curve will become double inward. Therefore, here P total is equal to PA plus PB. If you get a graph like this, this is negative deviation from Raoult's law. One which shows negative deviation from Raoult's law. Therefore, to summarize what we have learned right now, I will put them in one statement like this. Binary liquids are classified into three types. One, solutions which obey Raoult's law, which are called ideal solutions. Solutions which show positive deviation from Raoult's law. Third one, solutions which show negative deviation from Raoult's law. Totally, there are three types of solutions. Second and the third cannot be separated because they will always give azeotropic mixture. Only the components of the first ideal solution can be separated by fractional distillation. This part should be known to you. With that understanding, we will now move to colligative properties. I will try to just give highlights of these colligative properties. What are colligative properties and speciality about this? I will write on the top colligative properties. Colligative properties. What are colligative properties? Colligative properties are those which do not depend upon nature of the solute, depend only on number of solute particles present. Number of solute. Do not depend upon nature of solute. Do not depend upon size of the solute particles. Only depends upon number of solute particles. One properties which depend on number of solute particles do not depend upon the nature of solute particles. Size of the solute particles are called colligative properties. How many are there? 4 of them. Relative lowering of vapor pressure. It will be given as P naught minus P divided by P naught. Second, elevation in boiling point, delta TB. Third one, depression in freezing point, delta TF. Fourth one, osmotic pressure. Osmotic pressure. Osmotic pressure is 5. These are called colligative properties. Therefore, many a time they will confuse. They will say, vapor pressure, is it a colligative property? No. Lowering of vapor pressure, is it a colligative property? No. It is relative lowering of vapor pressure is only colligative property. Elevation in boiling point is a colligative property. Boiling point increases. Depression in freezing point is a colligative property. Osmotic pressure is a colligative property. Please remember this. There is what will happen to the vapor pressure when solute is added to a solvent. Vapor pressure decreases. Please remember. Therefore, vapor pressure of the pure solvent is more. Vapor pressure of the solution is always less. Vapor pressure of the pure solvent is more. Vapor pressure of the solution is less. Divided by vapor pressure of the pure solvent is called relative lowering of vapor pressure. There is also a Raoult's law. What the Raoult's law says? Raoult's law says relative lowering of vapor pressure for a non-volatile solute. Please remember, solute should be non-volatile, is equal to mole fraction of the solute. This is called Raoult's law. This Raoult's law is different from the Raoult's law of binary liquids. Here solute is there. Relative lowering of vapor pressure obtained by dissolving a non-volatile solute is equal to mole fraction of the solute. This is called Raoult's law. Therefore, I can write now P naught minus P divided by P naught is equal to mole fraction of the solute is nothing but number of moles of a solute divided by number of moles of solute and the solvent. This is same as this. This is solute, N2 is solute, N1 is solvent. Now, for a dilute solution, N2 is very much smaller than N1. Again, this formula becomes P naught minus P divided by P naught will be equal to what? N2. Denominator N2 is very much smaller than N1. Therefore, I will write it as N1. P naught minus P divided by P naught is equal to N2 by N1. Now, if you go one step further, it could be written as P naught minus P divided by P naught is equal to, instead of N2, you write W2 by M2. And you write this, the N1 as W1 by M1. This will be equal to W2 M1 divided by W1 M2. I can easily find the molecular mass of the solute by using the formula W2 M1 divided by W1 into P naught minus P divided by P naught. This is the formula to find the molar mass of the solute using Raoult's law. I will quickly go through the remaining parts. Elevation in boiling point. Delta TB. When a solute is added to the solvent, boiling point becomes more. Boiling point of the solution is more than, solution will have higher boiling point. Solvent will have a lower boiling point, T minus T naught. That is called elevation in boiling point. Always boiling point increases when you put the solute in the solvent. Please remember. Why it increases? The reason is vapor pressure. Here you notice, I will put vapor pressure. This I will take here. One graph will go like this. Another graph will go like this. What will happen is, what is boiling? Boiling is the case where vapor pressure becomes equal to atmospheric pressure. This is atmospheric pressure. When vapor pressure becomes equal to atmospheric pressure, it boils. This is for pure solvent. This is for solution. Solution will lower the vapor pressure. Therefore, what you notice here is this is temperature. Here, if you write a straight line, you will get temperature. Here, if you write a straight line, this is a different temperature. Therefore, this temperature T, this is T naught. T is higher than T naught. This is called elevation in boiling point. And elevation in boiling point can be calculated using the formula Kb into M, where M is called molality. M is molality. In my very first or second slide, I said this. M is equal to molality. Kb is called molar elevation constant. Molar elevation constant, or it is called ebullioscopic constant. Constant. That is Kb. And Kb for water, please by heart, is 0.52. Kelvin kg per mole. If you do not remember any other value, remember only the kb value of water. kb for water. kb is this. Then, do you have another formula by which you can calculate delta TB is equal to, remember this formula, 1000 kb W2 divided by W1 M2, where kb is called molar elevation constant, Wt is the weight of the solute, W1 is the weight of the solvent, M2 is the molar mass of the solute. You can calculate M2 if you know delta TB. M2 comes here, delta TB comes here, you can easily calculate molar mass of the solute. This is about elevation in boiling point. Very similarly, you can go for depression in freezing point. We are winding up. 5 more minutes I will take and try to wind up the session. Depression in freezing point. Will be given as delta TF. What happens? That means when a solute is added to the solvent, freezing point decreases. That means delta TF should be T0 minus T. T should be less than T0 when you add. This is called depression in freezing point. Why it happens? I will explain with the graph. I said there is a graph like this. There is a graph like this. This is for solute. Pure solvent, no, solute, no, solvent. And this is for solution. Two graphs. This is where they will meet, I was telling, and this is boiling point. Now freezing point comes here. This is the freezing point. You have a graph like this moving. Forget about this. Here. And this graph will reach here, somewhere here. Now this is the pure freezing point of the pure solvent. This is the freezing point of the solution. I'm not able to draw straight. You should draw straight. Okay. T will be less than T0. That is called depression in freezing point. This is vapor pressure curve of the solid. This is the vapor pressure curve of the solvent. This is the vapor pressure curve of the solution. That will meet lower and therefore freezing point is less. Therefore, you have delta TF is equal to Kf into M, where M is the molality. Kf is called molar depression constant. Or cryoscopic molar depression constant or cryoscopic constant. The value of Kf by heart is 1.86 Kelvin kg per mole. The delta TF can be calculated using the formula 1000 Kf W2 divided by W1 M. Yes. Dear students, we have covered a lot under solution chapter. Colligative properties, I shall just mention few of them. Colligative properties are those properties which do not depend upon nature of the solute particles, size of the solute particles, only number of solute particles it depends. Only depends upon number of solute particles present in the solution. Which are the 4 colligative properties? You should remember. Relative lowering of vapor pressure, elevation in boiling point, depression in freezing point, and osmotic pressure. I have covered 3 of them. Osmotic pressure is pending and little more is pending, but most of the things of this topic are covered. Please remember, with one point I shall just wind up. For example, sodium chloride is dissolved in water. what will happen to the boiling point? Boiling point increases or decreases? Boiling point increases, because sodium chloride will give you 2 ions. One sodium chloride will give 2 ions. That is why boiling point increases. Sodium chloride dissolved in water, freezing point decreases, because depression in freezing point is what we have learned. Students, it was a pleasure teaching you the solution topic. Please go through the topic again. Go through the textual material which is there in the CBSE text, which is provided by the Karnataka board. Go through that, try to work out all those problems and try to understand the topic well. Thank you very much.
Thank you, sir.
Thank you.
Sir, one student asking, please repeat the molarity ಅಂತ ಕೇಳಿದ್ರು.
ಕೇಳಿದಾರಾ? Okay, ನಾ ಹೇಳ್ತೇನೆ. Molarity is number of moles dissolved in a liter. I am giving some examples. Let us say sodium hydroxide, Na is 23, O is 16, H is 1. Together become 40. 40 grams is 1 mole. If I dissolve 40 grams in 1 mole, it is called 1 molar sodium chloride. 40 grams dissolved in 1 liter of the solution is becoming 1 molar solution. Therefore, to make 2 molar solution, what should I do? 80 grams should be dissolved in 1 liter. 2 molar solution ಆಗ್ತದೆ. 0.5 molar ಆಗಬೇಕಾದ್ರೆ 20 grams dissolved in a liter. How do you find molarity? Let us say I will give you a problem. 20 grams dissolved in 200 ml of the solution. Find the molarity of sodium hydroxide. What you do is 20 grams is present in 200 ml. In 1000 ml, how many grams? Find out. 20 into 1000 divided by 200. Do it. 20 into 5, it becomes 100 grams. 100 is a dissolved in liter divided by molar mass, 40. 100 divided by 40 becomes 2.5. Molarity is calculated like that. Therefore, I repeat again, molarity is calculated by knowing the mass in a liter. Whatever is the mass given in 100 also, in liter how much you have to find. Mass is given in 100 ml, let us say 10 grams. In 1000 ml how much? 100 grams. 100 grams divided by molar mass, divided by molecular mass will give you molarity. Am I clear? I have tried my best to answer.
And one more question from Tejaswini. How does molarity varies with the temperature?
Yes. Listen, molarity varies with temperature because volume it depends. 1 liter. As the temperature increases, volume will also change. Volume is not a constant of a solution. Volume is not a constant. Mass is a constant irrespective of the temperature. Mass will not change with temperature. Volume will change with temperature. Therefore, molarity will change with temperature because molarity is moles dissolved in a liter. Liter is the volume. When it depends upon volume, it changes. When it does not depend upon volume, it depends only on mass or number of moles, then it is independent of temperature. For example, mole fraction. Mole fraction doesn't have volume. It has number of moles of the solute, number of moles of the solvent or solution, numerator and denominator. Therefore, number. Therefore, it is independent of temperature. Molarity is also independent of temperature. Molarity only depends upon temperature. Any other question?
One more question from Uma.
Yes.
How to react Vant or factor? She asking.
What is that?
How
Vant
to
of
react-
factor. I have not
Yes.
touched that. Yeah. Vant of factor, I was not able to touch upon that. Since you have asked, Vant of factor is called I. I will answer it. I is called Vant of factor. number of particles present in the solution divided by number of particles, theoretical number of particles, if there is no dissociation or association. I will explain. Sodium chloride, if I dissolve it in water, how many ions it would give? Sodium 1 ion, chloride 1 ion. Therefore, numerator number of ions will be 2. Sodium chloride, if it is not dissociated, number of particles would be 1. Therefore, I will be 2 by 1. Number of particles dissociated divided by number of particles as if there is no association or dissociation, 1. 2 by 1 will be 2. Therefore, I is equal to 2 for sodium chloride. Can I do it for barium chloride? Barium chloride gives how many ions? 3 ions. Therefore, I is equal to 3. Provided they dissociate completely. If they do not dissociate completely, I will be always a fraction because there is a degree of dissociation alpha. Alpha is the degree of dissociation. There was one question, I read it on KH. I will answer that. You just see this. P is equal to KH into X. There is a formula. This is called Henry's law. P is equal to KH into X. If P is constant, KH and X are inverse to each other. KH is higher means X should be lower. So that pH is a constant. Therefore, higher the KH, lower will be the X. Means lower is the solubility. Therefore, which gas dissolves more is a question. Let us say noble gases. I will give an example of noble gas. Helium, neon, argon, krypton, xenon, radon. Radon you leave. Remaining 5 you take. Helium, neon, argon, krypton, xenon. Xenon dissolves more. Therefore, KH will be less for xenon. Helium will be dissolving least in water. Therefore, helium will have highest KH. Higher KH for lower solubility, lower KH for higher solubility. I have answered that question. Any other question?
No, sir.
Okay. Thank you very much for the opportunity that given to me. I have tried to do my best in the time that is allotted. Thank you very much.
Thank you very much, sir. Today I have to give very informative talk on solutions. So on behalf of KSTA and myself, once again, I thank you, sir.
Welcome. Thank you very much.
So I thank you, my Academy Chief Executive Officer, Dr. Ramesh sir, and academic colleagues, and our director, and all the attendees. Once again, I thank you, sir.
Thank you. Thank you very much.
ಸೊ ವಿದ್ಯಾರ್ಥಿಗಳೇ, ನಾಳೆ ಮತ್ತು ನಾಳಿದ್ದು ಯಾವುದೇ ತರಗತಿ ಉಪನ್ಯಾಸ ಕಾರ್ಯಕ್ರಮಗಳು ಇರುವುದಿಲ್ಲ. ಸೊ ಮತ್ತೆ ನಾವು 30ನೇ ತಾರೀಕು ಎಲ್ಲ ಸೇರೋಣ. ಹಾಗೂ ನೋಡಿ, ನೀವು 320 ಜನ ಆಯ್ಕೆ ಆಗಿರ್ತಕ್ಕಂಥ ಈ ವಿಜ್ಞಾನ ಪ್ರತಿಭಾಶೋಧ ಯೋಜನೆಯಲ್ಲಿ ನೀವು ಜಸ್ಟ್ ಒಂದು 60 ರಿಂದ 100 ಜನದಷ್ಟು ಮಾತ್ರ ಅಟೆಂಡ್ ಆಗ್ತಾ ಇದ್ದೀರಾ. ದಯವಿಟ್ಟು ಇನ್ನು ಮುಂದೆ ಯಾರು ಈ ಒಂದು ವಿಜ್ಞಾನ ಪ್ರತಿಭಾಶೋಧ ಟ್ಯಾಲೆಂಟ್ ಸರ್ಚ್ ಪ್ರೋಗ್ರಾಮ್ಗೆ ಸೆಲೆಕ್ಟ್ ಆಗಿದ್ದೀರೋ ತಾವುಗಳೆಲ್ಲರೂ ಕೂಡ ಅಟೆಂಡ್ ಆಗಿ ಈ ಒಂದು ಉಪನ್ಯಾಸ ಕಾರ್ಯಕ್ರಮವನ್ನ ಕೇಳಬೇಕು ಅಂತ ಮತ್ತೊಮ್ಮೆ ನಮ್ಮ ಅಕಾಡೆಮಿ ವತಿಯಿಂದ ತಿಳಿಸುತ್ತಾ, ಸೊ ನಿಮ್ಮ ಮಂತ್ಲಿ ಸ್ಕಾಲರ್ಶಿಪ್ ಏನಿದೆಯೋ ಅದನ್ನ ಪಡ್ಕೋಬೇಕಾಗಿ ತಮ್ಮೆಲ್ಲರಿಗೂ ಮತ್ತೊಮ್ಮೆ ತಿಳಿಸುತ್ತಾ ಈ ಒಂದು ಉಪನ್ಯಾಸ ಕಾರ್ಯಕ್ರಮವನ್ನು ಮುಗಿಸುತ್ತಿದ್ದೇವೆ. ಥ್ಯಾಂಕ್ ಯು ಸರ್, ಒನ್ಸ್ ಅಗೇನ್.
Thank you. Thank you very much.